previous lecture we have analyzed torsional vibration of some simple systems like single degree of freedom system or 2 degree of freedom system or 3 degree of freedom system. The problem in the methods which we covered till now is that if we want to analyze for larger systems like 4 degree of freedom system or 5 or 10 or maybe 100 degree of freedom system, then the problem comes whatever the algebra are needed to solve such problems are very cumbersome, and it's not key, we cannot able to solve them, but it is too cumbersome to and it is too time consuming. But there are some other methods available in which we can able to use the computer methods also, like we have two very strong methods which can able to handle any degree of freedom systems. One is the torsional there is transfer matrix method, which we will be studying next, and another method is there which is called finite element method, that maybe we will be studying subsequently. So in the transfer matrix method, generally what we do, we try to correlate the various states of the stations. Here state is representing either the angular displacement of the shaft or the torque which is acting at that particular location. So we will be relating these state vectors at various locations with the help of either field matrix, which is something like a stiffness matrix, and through point matrix, which is nothing but something like mass matrix or polar mass moment of inertia effect will be there in that. So this particular method, the advantage of the transfer matrix method is that even if the degree of freedom of the system is very large, then also there is the size of the matrices which we handle is remains same. There is another method that is called finite element method. In that the problem is if the size of the matrices which we handle increases with the degree of freedom of the system. But there are some disadvantages of the transfer matrix method, that the solution becomes nonlinear, and generally we get the frequency equations by which we will be obtaining the natural frequency. Their polynomial form, and the degree of polynomial increases as we increase the degree of freedom. So some kind of root searching technique will be using for solving those equations. But on the other hand, in the finite element method, we will be having large number of simultaneous equations. They will be linear and they can be solved using powerful techniques which are available in the numerical analysis. So let us see the multi-degree of freedom system of the torsional vibration using the transfer matrix method. So this is the multi-degree of freedom torsional vibration. In this, let us consider various numbers of discs which are connected by shaft. Here we are assuming that shaft is flexible but having no mass, and discs are rigid and having polar mass moment of inertias. We can able to consider any number of discs here, but for time being we are considering only 3 discs, but this method can be extended for any number of discs. These are frictionless bearing which is just supporting the rotor, so that it is not providing any kind of frictional torque to the rotor. So we are not considering the frictional torque onto the shaft, they are just supporting it, so that the frictionless motion between the shaft and bearing take place. These discs are having angular displacements, they are time dependent. Again here we are analyzing the free vibration, so we are not applying any force to the system. So let us take the free body diagram of one of the disc. Let us say disc 2. This is the disc 2. Let us say it is having this particular oscillation. Now because of this there will be torque on this side of the disc which will be coming from the shaft. Let us call it left of disc 2, torque left of disc 2, and there will be another torque from the shaft which is right of 2. So subscript R represent right, and there is back subscript R represent right, and L represent the left of the disc, and 2 represent the disc number. Okay. Now if we consider the equilibrium equations for this disc, we can able to write torque in the left of right of disc 2 minus left of 2, because they are minus because it is opposite to the displacement of the disc theta 2 should be equal to the inertia torque. Okay. So this equation is can be written as theta 2 plus like this. Now the angular displacement in the right and left of the discs are same, because we are considering disc as a is point. Okay. So these two equations, if you see carefully, in the left hand side we have kept terms which is having back subscript as right, and in the right hand side we have kept the terms which are having subscript L. So here, because both are same, so we can add back subscript to the theta here, that is L. Now these two equations can be combined in a matrix form like this. Right of 2 is equal to left of 2, and you will find that the first equation is representing theta in the right is equal to theta in the right left, and second equation is this has come because for simple harmonic motion we can able to write theta 2 like this. Okay. So that is taken care. So this particular matrix can be written in a more compact form as S, which is which represents the state vector, is equal to P2, which represent point matrix, and state vector left of 2. Okay. So state vector, you can see it contains angular displacement and the torque. So at one particular station we will be having two states, one is angular displacement and the torque, and from this equation you can able to see that we are transferring the state vector which is there in the left of the disc using this point matrix to the state vector in the right of the disk. Okay. Now we will consider the free body diagram of the shaft. Let us say we have taken the second shaft segment. So we have torque which is coming from the disk left of 2, and this is the torque which is coming from right of one disk. Okay. Now if we want to obtain the equilibrium equation for this, we can able to write that equilibrium equation. In that you can see that the displacement of the disk here is theta 1, and displacement of the disk here is theta 2, which is, let us say, left of 2, and this is right of 1. Whatever the torque is being transmitted through this shaft can be written as the relative twist between the two ends of the shaft into torsional stiffness of the shaft is torque. Okay. So this can be written as now we can able to see that because there is no disk into the shaft in between, so we will be having the torque in the right of 1 equal to torque in the left of 2. Okay. Now this particular equation can be combined. How we can able to combine? We can write these two equations in more convenient form, that is left of 2 is equal to right of 1, and theta left of 2 is equal to theta right of 1 plus torque right of 1 divided by the stiffness of the shaft. Now this particular equation, again, as we did in the previous case, we can combine in the matrix form. So we have state vector here right of 1, which is relating the state vector in left of 2, and this will take 1 by kt, 2 subscript we are keeping here, and then 0 1. So you can see that the last equation is representing the first equation of this, and the first equation is representing this equation. Okay. So this equation can be written in more compact form as F is the field matrix. This is the field matrix. Okay. So field matrix is relating the state vector which is there in the right of disk 1 to the left of disk 2. Now once we have developed equations, there is a transfer equation as the method implies, transfer matrix method. Using point matrix, we convert the state vector from left of the disk to the right of the disk, and from the field matrix we transfer the state vector right of the disk 1 to the left of disk 2. So that means we are transferring the state vector from one end of the shaft to the another end of the shaft. So using this transfer, whatever the transfer matrix we have developed, now we can able to relate the state vector from one end of the shaft to the another end of the shaft. Let us see how we can do this. So if we have a system like this in which various disks are here, these points represent the disks. So let us say 0, 1, 2, 3, 4, 5, all these are the disk locations. So we can able to write the, let us say, the previous equations I am writing here for this 2. So we develop state vector right of 2 is equal to point matrix 2 state vector left of 2. Okay. Also we develop this left of 2 is equal to field matrix state vector right of 1. So you can see that we can able to substitute this here, and so we can able to write state vector right of 2 is equal to P2 into F2 and state vector right of 1. So you can see that what we have done here, we are now transferring state vector from right of 1 of the disk to the right of disk 2. So directly we are jumping to the shaft and then disk in one shot, and the same thing can be extended for the whole shaft. Let us see how we can do it. We are writing state vector right of 1 as a U matrix, which is nothing but multiplication of the point matrix and the field matrix. Okay. So U represent the transfer matrix relating to state vector 1 and 2. Transfer matrix which relates station 1 and 2. Okay. So the same thing we can able to write state vector 2 right of 2 as transfer matrix 2 state vector right of 1. Okay. And you can see that here we can able to substitute this. So we will be having state vector 2 state vector 1 this. So what we have done here, we are transferring the state vector of 0th station to the state vector to the right of 2. So this can be extended even if we have n number of disks. So in that case we will be having state vector this transfer matrix n minus 1 like this up to 1 state vector this. So you can see that once we have developed the point matrix and field matrix, so we got the transfer matrix between two stations, and it can be used to transfer the state vector from 0th station to the last station, and this can be simplified as T, capital T, and capital T is the overall transfer matrix. This is the overall transfer matrix, and U was the transfer matrix between two neighboring stations. Now we will see how we can able to obtain the natural frequency from the overall matrix which we have generated. So what we did earlier, we obtained a matrix equation like this, which was relating the state vector from beginning, that is the extreme left of the shaft system, to the right of the shaft system. So if you see our previous figure in which we had 0, 1, 2 up to nth. Okay. So this is the state vector at 0 location, and this is the state vector at the nth station. Now let us expand this equation. Theta t we are writing in the expanded form, and if you see this T matrix, because it is multiplying various matrices, point matrices and field matrices, and all are having 2 into 2 size. So final also will be having same size because we are multiplying the matrices. So they will not increase in size, they will remain in size. So let us say whatever the multiplication, final terms are like this, and this is theta t, this is 0, left is not there because this is the beginning of the station. Now we need to apply the boundary conditions. So let us say we have for this particular case, let us say we have simply supported ends. Now to solve this particular equation, we need to apply the boundary condition, and if we see in this particular case, we have supported this rotor over the frictionless bearings. Okay, so they are not providing any torque in that. So that means ends of the discs are free. So here we have free end conditions. Free end condition means there will not be any torque at station 1 or station 0, and there will not be any torque at station n. So what we can do, we can equate this torque equal to 0, this equal to 0. These displacements will not be 0 because this free end, it will be having some displacements. So once we applied the boundary conditions for a specific problem in which we are considering the free end condition, you can see this equation can be expanded as this is the first equation. Second equation will give so you can see from the second equation, especially because theta naught cannot be 0 because there is a displacement of the disk which is there at the station 0. So it cannot be 0 because this is free end. So this quantity has to be 0. So that means t to 1, which is in fact function of omega n equal to 0. So this particular equation, which will be a polynomial in omega n, is the frequency equation. This can be solved if polynomial is more than 4th degree, then obviously we have to solve using some numerical technique. If up to 3rd, we can able to solve using closed form solutions. This second equation is that will be used to obtain the mode shape. So once we have solved this particular frequency equation, will depending upon the number of degree of freedom in the system, that means number of disks in the system, will be having that many number of natural frequency. Like if we have n number of disks in the system, rigid disks with the massless shaft, we will be having n number of natural frequency, and so here those natural for finding the mode shapes corresponding to each of the natural frequency, what we have to do, we have to come back to this particular equation, in which let us go to the next slide. Because this T11 is function of omega n. So let us say if we want to obtain the mode shape corresponding to first natural frequency, we need to substitute this here, and this can be taken as a reference, let us say is having value 1. Okay, so we can get the what is the displacement in the nth station. Now we have relations earlier using transfer matrix method, in which we have related the state vector of the nth to the state vector of the n minus 1. Okay, so we can able to use those equations like state vector so these relations can be used, and here this is function of omega n1. Okay, so state vector at n minus 1 station can be obtained. Similarly, at n minus 2 and so on up to theta naught. So these are the relative displacements of various disks, and theta naught we have considered as 1. Okay, so these displacements which we obtained for a particular speed, okay, what we can able to do, we can able to plot them in this form, where this is the 0, 1, it will be having some value, 2, maybe it will be having some other value, like this up to nth, this is n minus 1 n. Okay, so this is the mode shape for a multi-degree of freedom system. In mode shape is nothing but the relative displacements of the various disks. So you can see that once we obtain the displacement of the shaft at one end, using transfer matrix we can transfer those information up to the other end. Okay, so this is corresponding to omega n1. Now similar mode shapes we can able to obtain for other natural frequencies 2 or 3. Just what we have to do, we have to carry out the same transfer matrix equations we have to use to relate various displacements corresponding to these natural frequencies. So in a particular multi-degree of freedom system, if we have n number of natural frequency, obviously we will be having corresponding n number of mode shapes. Now we have already seen how the transfer matrix method works. Let us see one example which we took earlier also, so that the concepts regarding the transfer matrix method is more clear. Okay, so we are taking for simplicity 2 mass rotor and polar mass moment of inertia of these are 0.06 and 0.02 kg meter per square. The diameter of the shaft is 0.1 meter and the length of the shaft is 0.6 meter. Now the modulus of rigidity is given as 0.8 into 10 raised to 11 Newton per meter square. With the help of diameter we can able to calculate polar moment of area, that is meter 4, and similarly the KT can be obtained as 1.31 into 10 raised to minus 10 raised to 6 Newton meter per radian. Now let us come to the transfer matrix, in which we have two stations, station 1 and 2, that is 2 disks are there, and the state vector of right of one disk can be written as, with state vector at 0th node, 0th station is here, station 1 is here, and this is related with only point matrix, because between 0 station and 1 only disk is there. Then coming to the state vector at 2, that is right of 2, is given as point matrix of disk 2, field matrix of shaft, and state vector right of disk 1. Okay, and we have already related this state vector with the state vector at 0 station, so we can able to expand this in this form. So here overall transfer matrix is multiplication of three matrices P1, F2 and P2, and for clarity I am writing these matrices so that the steps are more clear. This is the point matrix for disk 2, then the field matrix for the shaft, is this, then the multiplication of the point matrix for disk 1 minus here, minus will come here also in this place, then the state vector theta and t at 0th station. Okay. So you can see that three matrices are there here to be multiplied. If we multiply this, I am giving the final matrix so that the steps are more clear to us. This is the first element of the matrix, then this is the second element, third element is having slightly bigger expressions. Let us write that. This is KT, and the last IP2 by KT. So this is the overall transfer matrix. You can see that it contains omegas in various forms. Here it will be having the terms like fourth degree omegas. So now we can apply the boundary conditions. So boundary conditions is, because if we go back to the previous thing, this rotor is also supported on frictionless supports. So both the ends are free for this case also. So there is no torques at 0 station and there is no torque at this second disk right side. So both torques are 0, but displacements are not 0. So we can equate this equal to 0, also this equal to 0. So you can see that from the second equation, this term has to be 0. Let us expand this in the next slide. So after substituting values of stiffness terms and polar mass moment of inertias, we will be getting these terms. Is equal to 0. So this is this particular term which we equated equal to 0, and we substituted for various values. So you can see there is a polynomial in omega n and it can be solved, and one of the natural frequency is 0 because omega n can come common here. Another natural frequency will be obtaining is 9345.25, and you can able to see that this is the similar example which we have taken in previous lecture, and the results are the same, but methods are different. There may be some difference due to the truncation error, numerical truncation errors. Now regarding the mode shape, because natural frequencies are same, mode shape also remain the same. That means for first natural frequency, this will come, and this we can able to find out from the previous expression, the same expression. You can substitute in this equation, the whole equation, omega n is equal to 0. So you can see that theta, which is right of 2, will come equal to theta naught. That is, this is in more explicit form, this form, okay. And other intermediate displacements also can be checked through the transfer matrix method, or transfer matrices, in between transfer matrices, and you will see that all the displacements will be having same value, because corresponding to the 0 natural frequency we will be having all the displacement equal to 0, that is rigid body mode. Similarly, if we substitute this in the previous equation, we will be getting relative displacement, that is 2 by theta naught is equal to -3. Again we will be getting the similar as we got in the previous case. Now we will be starting another class of torsional vibration, which is a part of the geared system which we have covered. In the geared system, we have seen that the two shafts are having different speeds, and we could able to convert that system to equivalent single shaft system. But there are some application where we will find that the same gear, one common gear, gives power to 2 or 3 shafts. Especially in cotton industry, we will find that there will be a common power source, and various spindles will be given power from that, and because of that the power goes to various branches, and that is why we call this particular system as branch system. And this particular case will be analyzing for two branches, and the method can be extended for any number of branches. And here we will be using transfer matrix method for this particular case. So let us see what is branch system. So we have one particular shaft, it can have various discs, and then this is the last one is gear, and it is transmitting power to another shaft. Let us say this is a branch A, this is branch B. It can have 0 to n number of discs. Similarly, here also it can have various number of discs. Then there is another branch which is coming out from this, from the same gear, that is, let us say, branch C. So what is happening, we have a branch A from where power is going to branch B, also to branch C. Now our aim is to find out how we can able to get the natural frequency of this system, so that we will be knowing whether whatever the resonance conditions, whether we can able to avoid in this particular system. So as I told, we will be using transfer matrix method, and we already analyzed transfer matrix method for a particular branch. When there is a single shaft, we can able to write the state vector for that particular case like this. Let us say this is a branch A. This state vector is corresponding to the nth disk here, and let us say A is the corresponding overall transfer matrix for this, and this is the state vector at the beginning of the branch A. Similarly, we can able to write the state vector of nth disk of branch B here with we can relate with the state vector of branch B to the at 0th location. Let us say B is the overall transfer matrix for that branch B. Similarly, we have branch C, so we can able to write this overall transfer matrix relation for branch C. Okay. So, what we will be doing, we will be taking, let us say, the first equation, and we will expand this, because those three equations at present are independent. Now, what we have to do, we have to find out the condition at the junction from where we are transferring power from one shaft to another shaft. What are those conditions? Based on that, we will be linking these equations basically. So, let us take branch A and expanded form of that equation is, let us say, A11, A12, A21, A22. These are the matrices for corresponding to capital A. Then here we have state vector at 0th location. Let us take 1 as this value, we are taking as a reference value, that is theta naught A we are taking as reference value 1, and because that particular end of the shaft is free, so we are taking torque as 0. Where this is free, there will be no torque in this. So, from this we will get theta NA is equal to A11, and from second equation we will get TNA is equal to A21. Okay, this is coming from these two equations. Now, let us come to the branch B. In branch B, how we can able to relate the branch A and B? With the help of gear ratio, we can able to relate the displacement at 0th station of branch B to the nth station of branch A by the gear ratio between branch A and B. This is the gear ratio. Now, what is the other condition in branch B? Because the right hand side of the branch B, that means here there is a free end. So, we will be having torque in the nth station of branch B is equal to 0. So, these are the two conditions we have, which we need to apply in the second equation of this particular equation. So, let us expand this equation, and if we expand it, it comes theta, this is for the nth of B. So, this torque is 0 here, according to this should be equal to, we are expanding for capital B, these are the elements of the matrix. Then here we have theta naught B, so that can be written in terms of theta NA by gear ratio NAB, and torque remains the same. This now these equation can be expanded, and B, that is the first equation, B11 theta NA by gear ratio AB, then we have B12 and T B naught. Okay, and second equation of the previous this expression will give us B21 theta NA NAB, then B22 T B naught. Okay. Now this second equation can be you can see that from this second equation we can obtain the torque at 0th station. Okay. So this is B21 divided by B22 theta Na by gear ratio AB. Okay. So this expression we got, which is the torque at 0th station of branch B. Okay. These and from the first equation you can see we can able to substitute this here, so that we can able to eliminate the theta naught B from the first equation here. So let us, if we do it, then it will be containing only the displacement at branch A, the last station of branch A, here also. So you can able to see that this particular equation will be containing only the displacements that will be using in future for obtaining the mode shapes. So now let us come to the branch C. We already covered the branch A and B, we related them also. Now from branch C, what we can able to find out. So at branch C we have similar relation as branch B. First thing is with the gear ratio between A and C. Okay. And apart from this, there is another condition which is coming from the how much strain energy is transferring from gear A to B and C. So if we equate that, we will get a relationship of torque which is transmitted through A and B and C. This is this torque C. Okay. So these two conditions we have to satisfy at the branch, for the branch C. Okay. So these equations, if you see carefully, can be written as theta Na we already obtained earlier, that is equal to A11 by NAC, and then the second equation, this equation we can able to write in this particular form, in which we want to know the torque at station 0 in branch C equal to, okay, just we are transferring other terms in the other side, so that we get the expression in terms of known quantities. So here you can able to see that we have the expression for T naught B earlier. Let us go back to that previous slide. T naught B is this one. This can be written as B21 theta Na is nothing but A11 divided by B22 and AB. So this expression will be putting here, and if we substitute that, we will find this particular form of the equation. So basically here we have eliminated all the torque terms, and now they are in terms of the overall transfer matrix for branch A, B and C. You can see A11, B21, B22, all these are related with the overall transfer matrix of the branch A and B, and NAB is the this gear ratio between branch A and B. Now we will be writing the equation for the expanded form of the equation for branch C. Here theta is for branch C, because free, this particular end of the shaft is free, so torque is 0, is equal to, these are the elements of overall transfer matrix for branch C. Then here theta naught C is there, which we have obtained like this. So we will be substituting this value directly there, A11 by NAC, and here theta naught C is there, which we will obtain expression. So this quantity will be directly substituting here. Okay. So once we are substituted here, from the second equation we'll get a equation of this form, which is nothing but the frequency equation of this branch system. There is a slightly bigger expression, but for completeness I am writing this. So you can see this particular equation, which is frequency equation. In these A's, B's and C's all contain omega n, and so here we will be having something like a polynomial in terms of omega n, and they can be solved if it is up to third degree, we can able to solve closed form. Otherwise, we have to go by for numerical techniques for solving the polynomial, and depending upon the number of disks we have in the system, that many number of natural frequency will be getting, that many roots of those polynomial will be getting. Okay, and then once we got the natural frequency, then again we have to go back to these transfer matrix equations, so that for a particular natural frequency we will be substituting various terms, like here all C's are function of omegas. So we will be substituting here, so we will be getting the displacement at nth station of C, and then using other transfer matrix method, as earlier also it has been explained, we can able to obtain the relative displacement at various stations. So that method is already explained in the previous discussions. So I am not repeating that same thing here. Now we will be taking one example of the branch system, so that our concepts are more clear, and especially I will be taking very simple example, so that the more focus is toward the clearing the steps rather than complexity of the problem. So in this particular case I am taking a very simple branch system, in which this is a branch A and this is the gear B, and here two gears are connected, one is C and another is D, and this particular shaft is connected with a disc E, and this particular shaft is connected with a disc F. So here we are neglecting the mass moment of inertia of the gears C, B and D. This disc A is having mass moment of inertia, polar mass moment of inertia. This disc E is having polar mass moment of inertia, and this is also having polar mass moment of inertia. They are having the following values: 0.01 kg meter square, then is having 0.05 kg meter square, and the disc F is having 0.06 kg meter square. The gear ratio between B and C is 3, and gear ratio between B and D is 4. So these are the gear ratio given, and various diameters and lengths of the shafts are, like all the shafts are having 1 meter length. For simplicity we have taken like this. All the shaft is having 1 meter length, and diameter of the AB shaft is 0.4, that is this particular shaft and diameter of the second shaft, that is here, is 0.2 meter. They are all in meter. And diameter of the third shaft is 0.1 meter. Now the modulus of rigidity is 0.8 into 10⁻11 Newton per meter square. Now what we can do, we can write the transfer matrix for the branch A. That will be multiplication of the field matrix, that is of shaft AB, and point matrix of shaft A. Okay, field matrix and point matrix. Then that particular terms can be multiplied. I am giving the final form of that matrix, that is FAB, and PA is given as, if we substitute the values here, we will get this. Okay, so this is the, I am expanding it so that the method is more clear. I am expanding this because method should be more clear. And for branch B, similarly we can able to write point matrix and field matrix of the shaft CE. Okay, and this particular, if we substitute the values, we will get here 00 and here -3 7 10⁻⁻10 omega NF plus 1. Okay, similarly we can get the overall transfer matrix for C matrix as point matrix for B and field matrix for BF, that is having this form. And last term is +1. Okay, so here we got all the three matrices. We got three matrices for A, this is the A, and C. So we know all the terms of A's, B's and C's. Now we can go to the frequency equation. Frequency equations in the more simplified form is of this form. This plus another term, so you can see that this equation is nothing but a polynomial in terms of omega, because all these terms contain omega, they are the elements of the matrices. So if we substitute various values from the previous matrices, we will get a polynomial of this form. Minus 1.2 10⁻⁻19 omega 6n. is equal to 0. So this can be solved for omega n. So you can see that there will be 3 roots. First will be this, second is, then third is, okay. So you can see that the method is very clear now for finding the natural frequency. The mode shapes can be obtained. We have to go back to the various transfer matrices. So in this particular lecture we have covered the transfer matrix method initially, and for the single shaft system. Then we extended the method for the branch system also, and through numerical example we try to clear the basic concepts, especially with the help of very simple examples.